Hi everyone, this is GKCS. I'm going to be sharing one of my favorite problems with you today when it comes to interview preparation. It deals with binary search trees and it deals with combinatorics. Hey, stop making me small. Yeah. We have an array given to us. This array has n elements, and the range of these elements is from negative infinity to positive infinity. So they're unbounded, but they're integers. Okay, and let's assume that the numbers are 2, 0, -1, 4, 3, 7, 1, 8. Okay, so using this, we have to actually construct a binary search tree. If you take this array as an example, you're going to get something like this. The first element is 2, which is going to be mapped over here. Then you have 0 going to the left hand side of it, over here. You have -1, which is even smaller than 0, so that comes over here. 4 goes on the right hand side of 2. 3 comes to the left of 4. 7 goes to the right of 4. We have 1, which is really small compared to 2. I mean, just a little smaller, so it has to go on the left hand side of the subtree. It'll come over here. And finally, we have 8, which is the largest element, comes over here. Okay, so this is a binary search tree. The property of this is that for every node, you have all the nodes to the right hand side being larger than this node, and all the nodes to the left hand side being smaller than this node. Okay, that's true for every node in the binary search tree. That's why searches are efficient. What we need to do is we need to find the total number of permutations. So I'll call that valid permutations, okay, of the original array, such that we get the same BST. So if you want to construct a permutation of this array which ends up with the same BST, that is considered a valid permutation. For example, if we take the original array over here and just copy that 2, 0, -1, 4, 3, and let me jumble up 7, 1 and 8. So I'll make it 1, 7, 8. The binary search tree I'll get up till this point will be the same. So up till this point is the same. Then I have 1, which goes on the left hand side, and things are fine. So 1 is fine. 7 again is fine. It'll come over here, and 8 will be fine. It'll come over here. Okay, they're both the same. Structurally, they are the same. All the values in all the positions are the same. So these two trees are effectively equivalent. Okay, so that will be a valid permutation. On the other hand, if I take the order and I jumble the nodes a little bit, so let's say 2, 0, -1, 3, 4, and then I take the same order 7, 1, 8. So 7, 1, 8. The tree that I'm going to be constructing is 2, 0, -1. That all of this is correct, and then I have 3. So 3 is greater than 2, and it will come over here, and that will be a problem because this tree is no longer the same as the tree which was before it. It had a 4 over there. Now we have a 3. So this is an invalid permutation and should not be counted. Okay, our job is to find the total number of valid permutations of the original array, which are going to give us the same binary search tree. Okay, so let's try to see if we can find some properties in the solution which will help us build the overall solution. Firstly, we are seeing that some permutations are valid and some permutations are not valid. So let's try to find out when are permutations either valid or not valid. When we took 3 and interchanged the position with 4, there was a problem. But when we took 7 and interchanged the position with 1, there was no problem. Okay. Now let's look at the positions of 7 and 1. 7 lies over here and 1 lies over here. While the problem nodes, which was 4 and 3, like 4 lies over here and 3 lies over here. Okay. So we're getting a sort of an idea. Let's put it to the test. Take 2. try to change the position of 2. Try to make it over here, right? Interchange it with 0. Is that even possible? No. Anytime you take 2 and interchange its position with any other node in our binary search tree, the binary search tree structure is changing. I mean, basically the value of the root node is changing. So that can't be done. So 2 is fixed. There is no way it is changing. Okay. Apart from that, take this subtree out. Don't care about it. We have this part of the subtree, which is 4, 7, 8, and 3 over here. Can you change the root node of this subtree? 4. No, you can't. The moment you change the root node of the subtree, you're stuck. Okay. So what we are seeing is that the root node of every subtree is fixed. Okay. That gives us one observation. The second observation is that the order of 7 and 1, we could change that. Okay. Can we change the order of 8 and 7? No, because if you put 8 before 7 in the order, if you put 8 here, let's say, 8 will come in. We are going to see 2, 4, and then we're going to see 8 is greater than 4, so we are going to place the right node as 8, and our current subtree is going to change. So that's also illegal. And that was probably because we took 8 and 7, which lie on the same path to the root. Okay, they lie on each other's path on the root. How about we interchange 3 and 8? Okay, these two nodes are on different paths on the root, so that should be maybe fine. So that could be fine. Let's see. Let's interchange 3 and 8. We get 8 over here and we get 3 over here. The tree that we are creating is 2, 0, minus 1, which is even smaller. 4 comes to the right hand side, and now we have 8. 8 is greater, so we have a real problem because 7 has to be on the right hand side. So that didn't work either. Let's do another change. Let's put 7 here and 8 here. Now we'll have, instead of 8 over here, we'll have 7. After which we get 8, so it goes on the right hand side. Then we have a 1, which goes here. And finally we have 3, which goes on the left hand side. You're seeing that these two trees are again equivalent. So we are getting an idea. If you are lying on the same, if two nodes are lying on the path to the root, okay, they have a straight line to the root, they cannot be interchanged. Like we said, that is basically the first point, which is the root of any subtree cannot be changed. However, the nodes on the left and right subtrees can be in any order. Okay, why am I saying that? Well, for any node, if you pass in a node which is greater than that, it's going to go on the right hand side no matter what. Similarly, if you take a node and pass in nodes which are smaller than that, it's going to go on the left hand side no matter what. So the order of the nodes on the right hand side is not changing. That is the key to solving this question. Okay, so the nodes that you're pushing in on the left have no relation to the nodes that you're pushing on the right. So the ordering between them is irrelevant. However, the ordering within a subtree is fixed, like we said. Okay, so for any given node, you can push the nodes on the right hand side in a fixed order. You have to push the nodes on the left hand side in a fixed order, but the ordering amongst themselves can be in any way that you like. Okay, taking an example, take 4 here. The way that you insert 7 and 8 is fixed. The way that you insert 3 is fixed. But the position of 3 between 7 and 8 is random. So effectively, if I took the array 4, 3, 7 and 8 and constructed a binary search tree using it, 4 would come here, 3 would come here, 7 would go here, and then 8 would come here. I could take the position of 3 and put it anywhere I like in this tree, right? So 3 can come here, 3 can come after 7, 3 can come after 8, and it's fine because its position between 7 and 8 is independent of the ordering that they will get. So I can have the arrays 4, 3, 7, 8, that is one valid permutation. I can have 4, 7, 3, 8, that is another valid permutation. And I can have 4, 7, 8, 3, that is another valid permutation. So it can take 3 positions in the resultant array. So at the node 4, I'm taking the nodes on the left subtree and I'm taking the nodes on the right subtree and I'm trying to create a result. What is that result? I'll put 4 at the top of the array and I'll take left children and the right children and I'll keep the ordering between the right children the same and the left children the same. Okay, this is very important. I cannot change the ordering between them. However, I can mingle these two the way I like. So effectively, I have 2 strings of length m and n, which have causal ordering. They are ordered amongst each other, but there is no ordering between them. So A, B, C, D is one string, and I have 1, 2, 3, 4 as the other string, and I can make it A, 1, B, 2, 3, C, D, 4. Okay, this is a valid permutation. That's the basic idea. Now, for any 2 strings of length m and n, how many strings can you make which have this property? Well, basically you're constructing a fresh string of size m plus n, right? And in this string, you have to place m positions. Okay, take the first string, take those m characters and place them anywhere you like. So that would be m plus n cm. Once you have placed the characters A, B, C, D, let's say, that's it. That's all we can do. Because the rest of the characters, there are n characters remaining, and the second string is of size n, and the ordering in them is fixed. So it has to be 1, 2, 3, 4, 5. You cannot place 5 over here. That is illegal. You have to place 4 over here because the ordering is strict, okay, amongst each other. Similarly, of course, you couldn't have placed B before A. So you only have m positions in which you can place the first string amongst m plus n positions. So the answer to how many possible combinations you can make is this, which means that for any node having children like this, okay, right subtree and left subtree, this is of size m, this is of size n, the answer will be valid combinations for this node is equal to m plus n c of m, okay, and something else. The thing is, if you zoom into this subtree, there are multiple ways in which you can have 0, -1 and 1 come over here, right? So you could have made the combination like this. You could have made 0, 1, -1, and you could have made the combination in 0, -1 and 1. So there are multiple ways for you to create this subtree itself. Okay, so the total number of ways, the total number of valid combinations you can have for the left child should be taken into consideration, multiplied by the total number of valid combinations you can have for the right child, okay, the total number of ways in which you can create this triangle, into m plus n c of m is the total number of combinations you can have for any given node. Okay, and that is the recursive formula we have. So if the number of valid combinations for a single node is equal to 1, the number of valid combinations for an empty node is equal to 1 because emptiness is a valid combination, and those are the base conditions we have. The root node, like we said, is going to give us the final answer. All we need to do is just go to the left hand side and the right hand side, find the total number of valid combinations through this recursive function, and then multiply that by the total number of combinations we can make with the left and right children merging. And that is it. The solution to this problem depends on the recursive way in which we find the answer. We find valid combinations based on the total number of valid combinations that the left and right subtrees have, and then merge them together to create a single array, the total number of combinations for that is rather simple. We choose m positions amongst m plus n positions. Okay. Of course, looking at this on the whiteboard is much easier than actually solving it in the real world. However, I wanted to bring this problem up because a lot of people have issues when they're thinking about recursive data structures, especially when they're put together with combinatorics. So think about this problem. You might actually come up with a lot of insights while you're trying to solve this problem, or even while you're trying to understand the explanation. If you have any doubts on this, do let me know in the comments. I liked solving this problem, so I'm probably going to be taking more videos similar to this, which is on coming up with a solution which is elegant, short, and is all about the application of the right theory in the right place. Okay, until next time then, see you. What is system design?
System what? Can we get to the next question? Can I get a hint?
System design is the design of websites using systems.
System design. System design is the process of defining components and interfaces with their interactions based on specified requirements. Next question.